Okay. All right. So before we start the lecture today, maybe we should take about half an hour to discuss about our tutorial question because as you know, during the tutorial hour, we couldn't have enough time to discuss all the answers. So we use the slot just to discuss the answer only. So hopefully everyone has done the reading. Okay. So right now we have 24, 25, 26 students here. So where are the remaining 4 students? I think we have 30 students, right? Okay, let me share my screen. Okay, so here's the tutorial question. Okay, so let's see the question. So the first one, state the wave particle duality principle and state the relationship between the momentum F and the wavelength. So wave particle, it will be having the properties of the wave and also the property and the particle. So the momentum and the wavelength relationship, we just need to use this formula, then this will express the relationship. Okay, this is the way we solve the first question. So let's go to the second question. Okay, the work function of the material refers to the minimum energy required to remove an electron from the material. Assume that the work function of the gold, EGE, will be equals to 4.90 eV. Then cesium is 1.90 eV. Calculate the maximum wavelength of the light for the photoelectric emission of the electron for the gold and the cesium. Okay, in order to do this, anyone can give me the answer. Anyone? So maybe I pick some guy to answer this. Ng Wei Hong, what about the wavelength for the gold? What have you calculated for the wavelength of the gold? Yes, okay, 0.2353 micron M. Yep, something like this. But what about the cesium? Yongqie, what about the wavelength for the cesium? So you guys can know that since this one is dealing with the photoresist, so you just need to use this formula then to calculate the wavelength. That's it only. Okay, so let's wait for Yongqie's answer. Okay. Okay, Yongqie, are you here? Oh, you are typing the answer. Yes, Yongqie, are you here? Okay, maybe we choose another guy. So Yen Chang, are you here, So Yen Chang? Okay. 6.5335, which is around 6.54, I believe, times 10 to the power -5 cm or -7 meter. Okay, fair enough. So let's go to the third question. Calculate the de Broglie wavelength A equals to POH A equals to lambda, same thing. Then the electron with the kinetic energy of 1 eV and 100 eV. So maybe I pick someone to answer this. Li Zhelin, are you here, Li Zhelin? If you are here, then you type a yes first, then you only answer the question. Okay? What's the answer for the first A? The third A? For the both. Okay, 1.227 times 10 to the power -9. The one is for 1 eV, right? What about 100 eV? Okay, for the both. So for the rest of you, do you get the same answer? So I believe the answer should be all right. So let's go to a 3B. So if 3B, let's see who can answer me the question. Lu Jueming, are you here, Lu Jueming? Okay, what about the answer for 3B? Okay. So 2x6 times 10 to the power 11 meter, fair enough. So let's pick the other guy. Chua Yu Yang, 3C. Chua Yu Yang, are you here? Okay, what's the answer for 3C? (1.66 times 10 to the power -38). Okay, yep, correct. Okay, looks like everyone is fair enough. Okay, according to the classical physics, the average energy of an electron in an electron gas at the thermal equilibrium is 3 kT over 2, determined for T equal to 300K, the average electron energy, then the momentum, and also the de Broglie wavelength. So at first, you just need to use this formula to calculate the energy. After having the energy, you can calculate the momentum and also the de Broglie wavelength. Fair enough. So, Long Yao Ting, are you here? Mr. Long Yao Ting. Okay, Long Yao Ting seems missing in action. So let's pick the other guy. Brenda Coy, are you here? Okay, answer the next question. For the question 5, answer this. These three items: electron energy, momentum, and the de Broglie wavelength. Mm-hmm. 6.26. That one is the energy, right? The 6.26 is for what? Oh, the wavelength. Okay, I believe the 6.26 is the wavelength. What about the energy and the momentum? Okay, next time when you are trying to calculate the energy, maybe you can write in the EV form so that you can make things easier. Okay, and the momentum should be 1.06 times 10 to the power negative 25. Fair enough. Okay, energy should be 0.0385. Okay, let's go to the question 6. An electron and a photon have the same energy. At what value of that energy in dV will be the wavelength of the photon be the 10 times of that of the electron? Which means if some kind of the energy level, the wavelength of the photon will be times 10 of the electron. Okay, who can answer me this question? So let me pick up some guy. Lao Rokjing, are you able to answer this? Are you here, Lao Rokjing? No. Okay. Let's see any other guy. Ong Mei Ling, are you here? Miss or Mr. Ong Mei Ling? Miss. Okay, Miss Ong Mei Ling. Where's the energy level? Are you able to calculate this? No, also. Okay, seems like this one tricky a bit. So let's see how we're going to do this. Okay, so let me create one new. No. Okay. The electron and the let me close my WhatsApp. Having the same energy as the photon, but we know that the photon will be using the equals to HF equals to HC over lambda. And then for the electron, okay, the energy level is equals to half mv squared. Then you need to get the de Broglie wavelength. We know that mv equals to h over lambda. Okay, then v equals to hm over lambda. So this one is half m hm over lambda squared. Okay, just to plug in this to here only, nothing much. And then we also know that HC over lambda will be equals to the, it's a pure photon. And this one is the m h squared over 2 m squared lambda squared. This was the electron. M theta here, H theta here, and then C lambda P equals to the H2m lambda E squared. Okay, so let's check everything okay. Then in the question it also given hint that okay, the energy then the wavelength of the photon is the 10 times of the electron. 10 E equals to H2m lambda E squared. Okay, then we just make it simple, we remove one. So in short, your lambda E will be H over 2m multiplied by 10 over C. So in this case, you can know that your lambda is here. After you knowing your lambda is here, then you just can put back into the value, then calculate all the energy. So this is the basic way. So answer wise, let me see what's the answer. And okay, so your energy should be equal to 10.248 keV, which is the one given by the Yongqi. Okay, so this one, can everyone understand this? Boleh faham tak? Lalu boleh? Okay. Okay, cool enough. Give me 5 minutes. So let's continue. On meaning, can you understand this? Just now you say you cannot do it. Okay, then let's continue. Question 7. It is designed to produce the X-ray radiation with a wavelength of 1A. Through what potential voltage difference? The potential voltage difference is actually the kinetic energy, same thing. Must be the electron be accelerated in vacuum so that it can, upon colliding with the target, generate such a photon. Assume that all the electron energy is transferred into the photon. Okay, anyone can answer me this? Let's say, let me pick some guy. Ernest, are you here, Ernest? Yes. Can you answer me this question for the 7A? Cannot. Wow, so direct. Anyone can answer me this? Dear Leong Ho, what about you? Okay. Let's see how we can do this. Okay, let's put this side by side. So at first the electron is accelerated. Then we can know that the electron, it moves using the wave particle energy, which is a half mv squared. That equals to the EP. Because it's something like this. It's shooting an electron here, then emit a photon. Then the hint saying that all the electron energy is transferred to the proton, which means this will be equal to the EP. EP equals to C F over lambda. C over lambda, sorry. Typo. Okay. This design produces the extra of 1A, which means that this lambda is 1A. But you better make it into the all equals to the SI unit, okay? Because you are dealing with the SI unit in the dipole wavelength also. So in this case, it's 1 times 10 to the power negative 10 times H times C times 10 to the power of negative or negative 10. Okay, you know lah. 8 or 10, I forgot already. Then after that, when you are equal to this, then you can calculate the potential energy actually. So after this, B, by having this, will be equal to the EV also. Then you calculate the dipole wavelength. So who had already answered this? May I know that? If you know the answer, you type the answer. See whether you can get the correct answer or not in this case. Now, Lofting, what about you? You think you got the wrong answer? Okay, who do you get this value? The lambda for the B wavelength you get is 4.268. Okay, my lambda is, I get 1.1. This was a B, BB. For the A, is 12.4 keV. Anyone get this? For the energy? Yep. Don't see get the same answer as me. For the lambda, you should get 1.10 times 10 to the power of negative 11. Okay? Yihang, sabar. Relax. Okay? So this is how we do the answer. Do this question. So, any question at this moment? For Yihang, what happened to you? Okay, stop, Yihang. Otherwise, I need to kick you out.
Sir, I think can keep out. I think it's something wrong with him.
Seriously?
Yeah. I mean, the keyboard problem or something, I think.
Oh, okay. I thought he's paying enough. Okay, so let's continue for the lecture today. I have to stop him sending message first. Okay. So, Yihang, you better check your keyboard. See what is wrong with you. So let's see. Today we are going to do the before I proceed, I need to go back to the last lecture first because there's one or two slides I still haven't explained yet. Lecture 3. So this one can close. So this is the last time we discussed until here. We discussed the probability of the Fermi direct distribution. Okay, so last time we discussed about the conduction band, valence band, then maybe somewhere about the Fermi energy, somewhere in the middle, we get. Then the conduction band, valence band, somehow if the electron, it provides the energy, it will jump from here to here. Okay, so we need to find the probability of the finding the electron, let's say in this E level. So one of the formula for the probability is 1 equals to 1 plus exponential E minus EF over KT. Okay, so this is for the probability of finding the electron in the conduction band. Or there's another probability saying that we cannot find an electron in the valence band. Okay, E. So in this case, the probability is 1 minus 1 plus exponential E minus EF over KT. Okay, so these two formula we learned last week. Then we also consider some of the cases if the E minus EF is much bigger than the KT, then we can do the Maxwell-Boltzmann approximation, which means that the value will be approximately using this exponential negative E minus EF over KT. So it is one of the way to do it. So let me see here one example. So for example, this one, calculate the energy in terms of KT and EF at which the difference between the Boltzmann approximation and the Fermi direct function is 5% of the Fermi function. You might feel a bit confusing when it is mentioning this. What is this about? So let's see how we're going to deal with this. So there are two kinds of energy. The difference between the E Boltzmann, we put a EB, probability PB, minus the PF over PF is 5%, which is 0.05. Okay, and then so based on the language that we learned just now, the Maxwell-Boltzmann approximation for the probability is equals to exponential minus E minus EF over KT minus the normal one, 1 plus exponential E minus EF over KT divided this one, okay, to be equal to 0.05. Okay, so actually the slide is already given the answer. So when you're trying to multiply this thing up, this thing move to here, then you multiply this thing move to here, then you can get this. So eventually in the end of the story, your E minus EF will be more or less equals to the 3 kT. So this is how we deal with this Boltzmann constant, Boltzmann approximation. Okay, this is the content for the last lecture. So let's see the lecture for today. Okay, today we are going to learn about the semiconductor in the equilibrium. Every time before we provide any energy or any heat, if we didn't provide anything, the semiconductor will be in the equilibrium state. But what is the equilibrium? Okay, before that, last week we learned about the GE. You still remember we learned about all the integration GE, DE. Okay, then we came up with a lot of the constants. Then we try to see whether it's 1 eV to 0 eV. Then we put it, we do the integration, we get the value. That one is the GE. We also learn about the Fermi energy. So by definition, the Fermi energy is the highest energy when you didn't provide any temperature, or to be making more accurately, in the absolute zero temperature. What is the highest occupied energy level for the material? Okay, this is the two definition. So at first we need to deal with the equilibrium. Like I said at the beginning, there's no external forces such as a voltage, the electric field, magnetic, or temperature acting on the semiconductor. Which means something like this. If you are having let's say resistor, you are trying to make it open circuit. You didn't provide anything to it. Okay, that one. Inside this semiconductor, it will be having the electron. But how does the electron moving? That one we call it as an equilibrium status. Second one is the intrinsic semiconductor. Normally, in this semiconductor, we didn't add any impurities, no impurities. We call it as an intrinsic semiconductor. But if we add the impurity inside, what is the purpose of adding the impurity inside? The purpose of adding the impurity is to make it as a, let's say, more negative charge or more positive charge. So when we are adding the impurity, we call it as an extrinsic semiconductor. So what's the extrinsic semiconductor? It is the addition of the specific impurity atom to a crystal where the dominant charge carrier in the semiconductor can be either the electron and the conduction band or hole in the valence band. Which means that if originally, let's say, this semiconductor, it has the, let's say, 5 electron and 5 hole. But you want it to be more negative charge, then maybe you add the dopant of the electron, maybe S7. So that right now it becomes the N-type semiconductor, negative type semiconductor. But on the other way, if you add 10 hole, it will become a P-type semiconductor, positive type semiconductor. The one we call it as an extrinsic semiconductor. But today we are going to deal with the equilibrium and the intrinsic first. Okay, let me drink water first. So in the semiconductor, when the electron is moving, it will contribute to the current. Last time we also learned during the basic electronic, when we are trying to plug in the battery to the semiconductor or resistor, it will start moving somewhere around here. Okay, current actually is the rate which the charge flow. Okay, which means that maybe in certain time, how many charge has been flowing. Okay, that one you call as current. But the current in the semiconductor actually is determined by the number of the electron and the number of the hole in the valence band. So in order to know that how much electron is inside there, we need to calculate the density of the charge. Okay, do you remember that last time we learned the density of the state function? Okay, this one is the conduction band, valence band. We need to know what's the density so that we can know how much of the electron can be occupied inside here. Okay, we need to do the density. Okay, the density of the electron and the holes is related to the density of the state function and the Fermi direct distribution. So in the other word, we try to estimate the number of the hole in the allowed band. You might be confusing with this. So maybe take it as this. Imagine in the conduction band, okay, you have so big of the space, maybe from let's say 1 eV to 100 eV, for example. Then inside here, you maybe have an electron. After you're providing the energy, then you jump to here. Then you also can give the probability of the electron. Maybe in this stage is the probability. In this stage is the probability. The probability you are calculated using the Fe. Last time we done it right, using the 1 plus ESP, this one. So by multiplying the density, imagine that you have a density of state, GE. By multiplying GE and Fe, then you can roughly know the number of the electron. How does I say that? Imagine if you have a car park. Okay, this is a car park. Okay, so let's say there's a total space. Let's say there's a 40 total space. Then you also have a probability. Probability that maybe 1/10 is already occupied. So by multiplying the total space, T multiplied by P, then you can know that there are 4 cars or 4 car parks are occupied. Okay, same thing as a concept in here. Total space, imagine it as the density of the state. Then probability of the electron. So by multiplying density and the probability of electron, you can know roughly how much is the electron over there. Conceptually, can you understand this? Any question in this concept? Can you understand? Okay. Okay. Mr. Kwa, your keyboard okay already? Is it? Okay. The rest, can you understand the concept? Or you need me to explain again? Okay, no problem. So let's continue. So by knowing this, we can roughly know what is the number of the electron. Or to make it more precise, we need to know the distribution of the electron in the conduction band. Okay, but in the layman terms, we know that actually is the number of the electron. So the formula is like this. Number of the electron or distribution of the electron equals to the density of the state multiplied by the Fe probability. So this is the analogy that I told you just now. Total car park, possible number of the car that can number it, or maybe the probability of the car park being occupied. You can roughly know the number of the car, literally. Okay, so that one is the conduction band. But in the valence band, since valence band, we are using the other probability. Remember that G multiplied by 1 minus Fe. Because this one is to find the electron not inside there. When we are trying to using the, let's say the NE and PE, we always try to find the number of the electron or number of the hole. But when you know that, okay, number of the if electron jump to here, so there will be 1 electron and here's a 1 hole. Okay, but the probability of finding the hole is using this. So we just can use this GV multiplied by this. Then you can get your distribution of the holes. Okay, so this is the concept. But how are we going to apply this formula? we normally need to think how are we going to apply this formula instead of just reading all the theories only. So at first, we consider the intrinsic semiconductor. So an ideal intrinsic semiconductor is a pure semiconductor without any impurities atom. Like I said just now, the crystal is a pure crystal. You don't add any intrinsic semiconductor inside. But for the intrinsic semiconductor at T equals 0K, all energy state in the valence band are filled with the electron, and all energy state in the conduction band are empty of the electron, which means that if you didn't provide energy here, originally conduction band, no electron. This one, full with electron. And then the Fermi energy, EF, must be, is a mass, it's a constant rule, must be somewhere between the EC and the EV. EC is in this line, EV is in this line. It must be somewhere between this. Okay, when the temperature begins to increase above the 0K, the valence electron will gain the thermal energy, which means that if you are trying to provide the energy here, the electron will start shaking. When it starts shaking, if you're getting the energy, they will jump into here. Okay, so if there's an electron here, there must be a hole here. There must be always come in a pair. Unless you provide the additional electron into it, then it's a different story. But for the intrinsic semiconductor, it must be like this always. Okay, this part, any question? Can you understand? Everyone? Okay, so let's see. In an intrinsic semiconductor, the electron and hole are created in pairs. This one I mentioned already. Okay, let's see this diagram. Okay. We see the left-hand side first. So this one is a energy. EC is here. What happened? Okay, the one. EC is here. Fermi energy is here. EV is here. So you actually can see that the GCE will be in this shape. Okay. Then the GV will be in this shape, which means that when your EV is getting lower and lower, then your GV will be getting higher and higher. Then this one is the negative direction. We know that. This one, same thing. If you are getting higher and higher electron, higher and higher conduction band energy, then the density is getting higher and higher, which means it will keep increasing. Okay. And the probability, actually it will look something like this, theoretically. Okay. F is this probability. So by multiplying this point and this point, right now we multiply this point and this point, multiplying this point and this point, keep on multiplying. Then we will get a shape inside here. Okay. This multiplication is the number of the electron, or the other way around, we call it as the electron concentration. Same thing happened here, but right now we're using 1 minus, okay, 1 minus F. Multiplying, we'll get this area. This area, we call it as a hole concentration. So this one is the expanded view only. You expand it, then put inside here. Okay. Then the Fermi energy level is either in between it. It may be in the mid gap, or maybe it will be somewhere higher or somewhere lower than the mid gap. It depends. Okay, but it always must be between this energy gap, e.g., mid gap energy, band gap energy. Okay, right now, let's try to play around with the formula. Just now we have two formula, right? One is the anode, then GCFE. Another is the PO, GV, 1 minus FE. You can see this is a C, conduction band, the density of the conduction band, the density of the valence band. But we cannot just simply use the multiplication to get the answer we want. We cannot do it. because we know that this GC actually is a continuous one. So that's why in order for us to do this, we need to do the integration again. Okay, so GC, this thing we learned last time, this formula, we learned in the last week. This thing we also learned in the last week. Okay, then when you're trying to do the integration, we are trying to apply the Boltzmann constant. We want to make this part easier first, so that we don't have to integrate so many things. But after do the integration, but for here I won't show you step by step. Okay, the important thing that you need to know is this: your NO will be equals to this value. This is the ultimate equation that you have to know. Okay, so let me write the formula here. So the integration part, you can go back to integrate, no problem. But for my stay here, I won't explain it because it's too waste of time and it's not that important also. The important thing is the one. In order for us to find the electron concentration, or in the other word, we call it as a number of electron. The formula must be like this: 2 pi m asterisk kt over Planck constant square 3 to the power 2 exponential minus EC minus EF over KT. Okay, this is the ultimate formula that you have to know that. Then this thing can further simplify into NC exponential minus EC EF over KT. Okay, always remember this formula because we are always going to use it. But how are we going to calculate this? At first, we need to know how to calculate this. So for example, in this case, if there's a silicon, if you are given a silicon in the 300K temperature, okay, then in the conduction band, M asterisk MO equals to 1/08. Okay, just remember this. Last lecture, we had discussed about this. Okay, let me open this. Okay, wait a moment. So somewhere around here. Okay, 1/08. Okay. So let's get back to the slide. Okay. At first, we need to calculate the NC. This part. This part equals to NC. Okay. This NC, we will call it as the effective density function, which means that out of the so many concentration, what is the effective one? Which means it really contains the electron one. Okay, because it's effective density. And then let's see how we're going to play around with this. So 2 pi, no problem. Mn, we know that the Mn equals to the 1/08 MO. 1/08 MO. Kt. K is the Boltzmann constant. Okay. Then you try to put the value of the Boltzmann constant here first. But at this stage, you don't use the EB. You use the normal one in the Joule form, which is 1/38 times 10 to the power negative 23. 1.38 times 10 to the power negative 23. So this is T equals to 300K. And then this H will be 6.625 times 10 to the power negative 34. Okay, anyone can help me to calculate this value? Anyone? Try to calculate it and see what you get. Okay, once you get the answer, then let me know. Okay, what about the rest? Do you get the same answer? -25. Okay, fair enough. Any other answer? Okay, I believe most of you can get the same answer. It's 2.8 times 10 to the power negative times 10 to the power 25. But this one is a meter. Okay, meter minus cube. So normally, the lecture onward from now to the end, we are going to use all in the centimeter minus cube. So in order for you to convert to the centimeter cube, you should get about 19 cm minus cube. Okay. So basically, in order for us to do this, from lecture now, we will be keep on using this. And we're always doing this NC. And if we are going to calculate the PO, this one is the NO is the electron concentration. This one is the hole concentration. This one will be equals to 2 pi MP asterisk KT square 3/2, then exponential minus EF minus EV over KT. So in short, you can further written into MV exponential minus EF minus EV over KT. So right now we have the two major formula. One is the NO, one is the PO. Then you have the NC, MV multiplied by ESP, EC minus EF over KT. ESP minus EF minus EV over KT. So as you know, NC and ME, we need to use the above the super long formula to calculate every time. So to make your life easier, actually, these two values are always the standard value for the silicon and the gallium arsenide and the germanium. So somebody already helped you to calculate everything. NC will be equals to the 2.8 times 10 to the power negative 19. Then MV is a 1.04 times 10 to the power 19, all in the cm minus cube. But bear in mind that all the values are in 300K. Okay, back to the example just now. When I ask you to calculate, I am saying that this one is in the 300, and this one is in the normal form, not in EV form, not EV. Okay. So every time, for example, last time if you encounter something like this, encounter some question like this, next question. Calculate the thermal equivalent concentration of electron in the holes for a given Fermi energy. Consider silicon at T equal to 300K. Whenever when you see a 300K, you can straight away use the value for the NC and MV here. NC 2.8 times 10 to the power 19, MV 1.04 times 10 to the power 19. This is MV, sorry. Assume that the Fermi energy is 0.25 below the conduction band, and band gap energy is 1.12. Okay, interesting thing is, here, give you a few information here. Okay. This one, EC. Fermi energy level is 0.25. Then the band gap energy given is 1.12. Total up is 1.12 eV. So this thing in between here is 1.12 minus 0.25. So he asks you to find the electron and the hole concentration, which is a NO equals to the NC exponential minus EC minus EV, 0.25 over KT. KT, since above one is using the EV, below one must be using the EV. But one fun thing to know is 300K. So this is 300K, but we are using the KT. So K must be using the EV form, 8.62 times 10 to the power of -5 multiplied by 300. So this value is always equals to 0.0259. So we just need to hunt down 0.0259 every time when you are looking at the T equal to 300K. But if your T changes to, let's say, 500K, this thing must be changed. Okay, so NC, this NC you can obtain based on the table 2/8. You just need to replace inside there. Same thing happened here. PO equals to the MV, ESP. Right now, this one is the negative 1.12 minus 0.25 over 0.0259. Okay, MV also according to the table is 1.04 times 10 to the power 19. So by replacing all the value inside there, you can very fast get your answer. And your answer must be in the centimeter. Okay? Any question at this stage? Any question? Still following? Okay. For the rest of you, can you follow? Okay, maybe you try one more example here first. Okay, let me for this. Imagine your EC and EV. EF, EV. Let's say this one is a 0.34. This one is a 0.12. Okay. Then under the 300K for silicon, calculate the NO and PO. Okay. Then use this two value, NC and NV. Then your formula will be NO equals to the NC exponential minus EC minus EF over KT. PO equals to the MV exponential minus EF minus EV over KT. Okay, let's try this. Okay, anyone? What's the value for the NO? Can anyone tell me? So basically, you just need to insert the thing inside there, then you can straight away calculate the answer already. Okay, we get the answer. Chanshu, yours was the electron or the hole concentration. Would you mind to tell us? Okay. So your NO is 5.572 times 10 to the power of 13. PO is 1.011 times 10 to the power of 17. For the rest of you, are you getting the same answer? Okay. So, Larochen, can you follow now? Okay, let's see. What about the rest of you? Yong Chi, are you getting the same answer? Okay, cool. Okay, so let's see the other type of question. So at first, he asks you to calculate the probability of the quantum state in the conduction band. E equals to the EC plus KT over 2 is occupied by an electron. So first thing we know, he asks us to calculate the probability in the E equals to EC plus KT over 2. And it's occupied by electron. So the probability wise, we can know that 1 plus exponential E minus EC over, E minus EF over then KT. Something like this. Okay. And then calculate the thermal equilibrium energy electron concentration in the silicon at T equals to 300 K, which is the NO. And then assume the Fermi energy is 0.25 below the conduction band energy. EF is equals to the EC minus 0.25. The value of the NC is 2.8 times 10 to the power 19. First, we settle this. But in this case, he assumed that he is using the Boltzmann constant, okay, the Boltzmann approximation. Okay, we try to use the Boltzmann approximation also. Minus E minus EF over KT. So E equals to the EC plus KT over 2 minus EC plus 0.25. So eventually, your value should be 3.9 times 10 to the negative 5. Then the electron concentration is the one that we learned just now. NO equals to the NC. NC is 2.8 times 10 to the power 19. Then exponential negative EC minus EF. EC minus EF equals to the 0.25 according to the given over here. And then this thing is in the 300K. Since it's a 300K, it's 0.0259. So eventually we get our answer. It's about 1.80 times 10 to the power 15. Okay, Maybe we take a short break. Also, you can do this question also. Okay, I will see you 10 minutes later. Okay, shall we continue? Okay, so can anyone tell me the probability? What's the answer for the probability? Okay, now Lofting is saying that the probability is 2.364 times 10 to the power 85 without approximation. Okay, without approximation. Okay, for the rest of you, do you get the same answer if you are using the without approximation? Long Yao Ting, are you here? What's the answer for the probability? Mm-hmm. You think it's too wrong? Okay, let's see the other guy. Lim Yong Chuan, are you here, Lim Yong Chuan? What's the probability that you get? Okay, is this the probability? Things are getting more interesting. Which formula are you using? Boltzmann or non-Boltzmann? What is this value about? Is this the probability or the concentration? Lim Yong Chuan. NO. Okay. So this is the NO provided by the Lim Yong Chuan. What about the probability that we get? Same, right? Let's keep. Okay, fair enough. So let's see. Go Kian Sing. What about you? What's the probability and the concentration that you get? Go Kian Sing, are you here? Anyone know where is Mr. Go Kian Sing? So every time when I ask a question, you guys better say a yes or something. At least let me know you are here. Okay. So, yep, Go Kian Sing, welcome back. So what's the answer that you get? Okay. The second one, the NO. Okay. So I believe your times 10 to the power of 21 should be, not 8021. And then yours one should be in the meter, not in the cm. So every time we need to change it to the cm. Okay, so I believe most of you can do it, no problem. So right now I want you to do one thing. Let's go back to the slide. So use this formula. Imagine that. Okay. So we know that NC will be equals to 2n mn asterisk kt h square 302. And then we also got this one value. Sorry. Okay. Okay. So right now we focus on the silicon part first, these two values. Calculate the NC of the silicon if T equals to 400K. Okay. Then second one is calculate the MV. So when you're calculating the MV, your formula should be 2 pi mp asterisk kt over a square 302. So second part is calculate the MV of the silicon if T equals to 400K. Okay, let's see what you get right now. So your H is equals to 6.625 times 10 to the power of negative 34. Then your MO is 9.11 times 10 to the power of negative something. Let me check back. Okay, negative 31. K is equals to 1.2, 1.38 times 10 to the power of negative 23. Okay, let me confirm the Boltzmann constant. Boltzmann constant is negative 34. Yeah. Okay, let's try to correct these two values, NC and MV, if T equals to 400K. Okay, anyone get the NC? Can anyone tell me? Let me pick some guy to answer this. Okay, Wong Ka Sing, what's your NC? If T equals to 400K. Okay, just do it first. So we will wait for the answer from you. Okay, 4.3357 times 10 to the power of 25. Is this in the, I think this one is in the meter if I'm mistaken. NC is 4.34 times 10 to the power of 25 meter mass cube. What about your NV? Okay, for the NC first, for the rest of you, are you getting the same answer as your friend Wong Ka Seng? Okay, all right. Okay, what about the NV? Chu Zhang Heng, can you tell me your NV? Okay, 1.62 times 10 to the power of 25 meter mass cube. Okay, for the MV, are you guys getting the same answer as the Chu Zhang Heng? Okay, good. You might be wondering why is the reason they asked you to calculate the one in the different temperature. Okay, let me tell you why right now. Okay, sometimes the question will ask you, okay, calculate the, let's say, NO at the T equals to 300K. So if the, let's say, EC minus EF is, let's say, 0.25, for example. But sometimes the question will ask you, okay, find the NO or the PO of the silicon if T equals to 400K. Then if the EC minus EF is equal to 0.25. Okay, if we are going to use this formula to calculate everything here, it should be a very tedious process. So lucky for you that right now we have the faster way to calculate this value. How are we going to calculate this value in fast? So by referring to this table, we know that all the temperature in the 300, the NC is 2.8, then the NV is 1.04. But all these are in the CM. So you can see that NC is 2.8 times 10 to the power 19 for the silicon if your temperature is 300K. But based on this 300K, you know that the 300 actually is to the power of 3/2, right? 302. But what if the temperature change to 400K? Okay, what is the value? So to make you faster calculate it, you don't have to every time use the formula. You can use this relationship to help you to calculate this. So let's see, if you want to calculate the NC in 400, one way to calculate is this one multiplied by this one divided by this one. So in short, your NC 400, you can write in this way. NC multiplied by 400 over 300, 3 over 2. Okay, so in this case, you can faster calculating this value. But back to the question, if he asked you to given this condition, okay, calculate the anode. T400K EC minus EF is 0.25. So how are you going to calculate the anode? So let's say you have an anode. It's the anode under 400 equals to the NC 400 multiplied by the exponential minus EC minus EF. Given by the question that EC minus EF is 0.25. Given by the question. 0.25. But the below one is equals to KT. Right now, you no longer can use the 0.0259 because the T is already changed. T is 400. One faster way to do it is 0.0259 multiply 400 divided by 300. Then you can replace the value and put it inside here. Okay, so like that, you can use a faster way to calculate all the relevant answer. Okay, or if you want to use the tedious way to calculate, no worry, you can go ahead, but it will take you sometimes. But if you want to use the faster way, also can, no problem. So maybe let's try one example here. For example, okay, no, not this. Okay, this one. Calculate the thermal equilibrium hole is at T equals to 400K. Assume that Fermi energy level is the 0.27 above the valence band. EF minus EV equals to 0.27 EV. The value for the MV at 300K is equals to 1.04 times 10 to the power of 19 cm minus Q. Then you are going to calculate the PO, thermal equilibrium hole concentration. So you need to calculate the MV, 400 over 300, 3 over 2, exponential, negative 0.27, 0.0259, 400 over 300. Okay, let's calculate this. Okay, what do you get for this answer? Anyone? Ernest, are you here, Ernest? Yes, what's the answer for the PO in the 400K? Okay, 6.43. Let's see the answer. Okay, the answer is already given in the slide actually. So you don't have to waste your time to do it. Okay, you can see that the way he answered the question is the one that I told you just now. Okay, so basically if you are using the same step, you are able to get the same answer. So maybe let's try this example for the example 4. So whenever when you see that MV is vary as the T to the power 3 over 2, it's because of the formula that we used in the earlier, because it's to the power 3 over 2. So that's why he written as the T vary according to 3 over 2. Okay, let's try this. So I believe the remaining value are all the same, just that right now it's just the temperature change only. Okay, what's the answer for this question? Anyone? Okay, let me check. Wang Chongyi, what's the answer for this question? Wang Chongyi, are you here, Wang Chongyi? Not sure. But what have you calculated just now? It must be something, right? How can you get a not sure answer? Okay, 2.36 times 10 to the power negative 10. Okay, seems weird. So, any other answer? Chia Tai Siu, are you here? What's your answer? So let's see. So this one MV is 1.04 times 10 to the power 19. How come all your answers are different one? So 250 over 300, 3 to the power 2. Then exponential negative 0.27, 0.0259 times 10 to the power. Okay, looks like everyone are having the same answer right now, which is the more convincing. So this is the doing step. You just need to put in everything, then you should be able to get the same answer as the rest of you. So since most of you are getting the same, so I believe there's no doubt. 13. Okay, cm minus cube. Okay, so for Long Yao Ting and Wang Chongyi, you might need to check the answer again. Okay. So we also have one thing, we call it as the intrinsic semiconductor. What is the intrinsic semiconductor? So intrinsic semiconductor, basically, you just need to multiply both together. Okay, multiply the NO and the PO together. Okay, so it do something like this. Okay, last time our NO is NC exponential EC minus EFI EF over KT. Then the PO is the MV exponential EF minus EV over KT. This one Ni square will be the NO multiplied by PO, because he assumed that in the intrinsic carrier concentration, the NO should be equal to Ni. The PO also should be equal to Ni. In the intrinsic semiconductor, then your F must be the Fi, intrinsic Fermi energy level. But how are you going to link all these things together? You want to create a formula that will consider the intrinsic semiconductor, intrinsic carrier concentration, and NC and NV. So one way to do it is to multiply NO and PO together. Then you get an Ni square. So in order for you to do this, you just need to do the NC, NV exponential minus EC minus EFI over KT exponential. This one is the EFI minus EV over KT. Okay, having this thing actually is the adding up together. Okay, So by having these two things adding up together, you can get your formula in this way. Minus Eg over Kt. Eg is the gap between the Ec and the Ev. Eg. Okay, last time we used to do this. We calculate this, then put it into the NO, calculate this, put it into the PO, then we get the NO and the PO. But right now, in order for you to calculate this, you just need to use this Ni square will be equals to the Nc multiply Nv multiply the exponential negative energy gap over Kt. Okay, let's see how we're going to use this formula. Okay, so for example, calculate the intrinsic carrier concentration in silicon at the 300K. We assume the 300K case first. Okay, so let's say if your energy gap is, let's say, 1.15 eV, let's say this is a silicon, the NC is 2.8 times 10 to the power of 19 cm cubed. Then your MV is 1.04 times 10 to the power of 19 cm cubed. Then this one T equals to 300K. Calculate the Ni. Okay? Use this formula. Okay, let's try to do this. So the Ni we call it as an intrinsic concentration, which means that what is the carrier concentration inside there by considering the Ni, NO and PO together. We consider hole and we consider the electron together. What is the intrinsic carrier concentration? This is what I mean. Okay, anyone get the answer for this case? What's your Ni? So basically, this is the last calculation for today. So let's pick some guy to answer this. Who Boon Kyung. Okay, 3.89. The rest of you, do you get the same answer? Okay. So I believe it's the same answer. Okay, let me conclude everything for today. First, last week we learned about the density. Then we also learned about the probability. Okay, by multiplying this and this, we can roughly know what is the number of the electron. Okay, but we cannot just simply do the multiplication. We need to do the integration. So after doing the integration, our NO will be equals to the NC exponential, the EC minus CF over KT negative. And the PO will be MV exponential minus EF minus CV over KT. Then your NC and MV can be calculated. NC will be 2 pi mn accelerate KT which square 3 to the power 2. Then your MV will be 2 pi mp accelerate KT over h square P over 2. Okay? So, when the T is changing, then the NC and the MV will be also changed. So that's why there's a one shorter way for us to calculate the new NC and new MV. That's the end. New, we put as a new. Equals to the NC multiplied by the, let's say, C over 300, 3 over 2. Okay? So we can calculate our new one, and new NO and new PO, something like this. Then eventually, this NO will be the electron concentration. This PO is the hole concentration. Okay, then the NC and MV is the effective mass, effective density. Originally, the G is just the density. The effective means that how much density is really occupying the electron. Okay, we call it as the effective mass, effective density. Then this one is the hole and the electron concentration, where you can treat it as a number of the electron or number of the hole in the conduction band or the valence band. So we need to consider the total one. For us to calculate the total one, we need to use the Ni square equals to the NO multiplied by PO. Okay, then we square root it. Okay, so this one is the intrinsic carrier concentration. Okay, so this is what we have learned today. Any questions so far? So as I mentioned before, everything just calculation. We just need to use the formula to calculate the information that we want. Any questions so far? Okay, I count to 3, 2, and 1. So if no question, I think that's all for today. I will see you by next class. Thank you everyone and have a nice day. Okay, bye everyone.